Meta may have just unveiled the future of language models. After watching this video, you might stop calling them large language models altogether. This is what we refer to as large concept models in the realm of language modeling and sentence representation. Essentially, it argues that LLMs may not always be the most optimal choice. In a new paper by Meta, they explore the concept of large concept models, which is somewhat different from LLMs. It's truly fascinating when you understand the problem it's aiming to solve. We're all familiar with LLMs, but if you understand how they operate, you'll know that they function through a process called tokenization. These systems predict the next word by analyzing tokens, which you can think of as an advanced form of autocomplete. I know some researchers might not be thrilled with me saying that, but in essence, that's how it works. To give you a better understanding, I've used the GPT-4 tokenizer visualizer to show what the characters look like to the LLM system. At this point, another AI researcher shares his thoughts on the topic, expressing growing confidence that tokenization may soon be a thing of the past. He suggests that the era of tokenization models could be coming to an end. He explains that humans don't think in tokens, which are hard-coded abstractions in language models, leading to unusual behavior. While language models can solve complex PhD-level math problems, they struggle to answer simple questions like whether 9.9 is bigger than 9.11. The researcher adds that Meta is now shifting language models toward large context or concept models, where token prediction is replaced by concept prediction. In this new approach, a concept is treated as a sentence that represents an abstract idea or action. The discussion highlights that while large language models, LLMs, have achieved undeniable success and continue to improve, they still lack a critical aspect of human intelligence: explicit reasoning and planning across multiple levels of abstraction. The human brain doesn't operate solely at the word level. Instead, we typically approach complex tasks by first planning at a higher level, like creating an outline, before filling in the details step by step at lower levels. Some might argue that LLMs are implicitly learning hierarchical representations, but the theory here is that models with an explicit hierarchical structure may be better equipped to produce coherent long-form content. This is important because LLMs tend to miss key reasoning steps, which could explain why certain models, like Claude, seem to outperform others in reasoning ability. It's possible that these models are already using a more structured architecture, although this is speculative. Nonetheless, companies like Claude have demonstrated an impressive level of response quality, leaving many to wonder how they manage to achieve such results. Let's break this down with an example they discussed. Don't worry about the large block of text. It's simpler than it looks. Imagine a researcher giving a 15-minute talk or presentation, similar to what I'm doing right now. In such situations, they usually don't prepare a detailed script by writing out every single word they plan to say. That approach wouldn't flow naturally, and the presentation would sound monotonous. Instead, researchers typically outline key ideas they want to convey. These are often summarized in a PowerPoint slide with just a few words or images, and they elaborate on those during the talk. Interestingly, if the same presentation is delivered multiple times, the exact words may vary, and it could even be presented in different languages. However, the core abstract ideas remain consistent. This principle also applies when writing research papers or essays. Humans typically start by creating an outline, a structured plan, and then refine it iteratively. This hierarchical approach is also used when processing long documents. Instead of reading every word, we remember specific sections where relevant information can be found and focus our search there. Here's an example to help illustrate the concept. On the left side of the diagram, you'll see how the model transforms a story about Tim into a simplified form. The pink dots represent the detailed story. It begins by explaining that Tim wasn't athletic, and he thought joining a sport might change that. He tried out for several teams but didn't make the cut. Instead of giving up, he decided to train on his own. The higher-level abstraction of this story is shown through the blue dots, summarizing the key idea. Because Tim wasn't athletic and couldn't join a team to improve, he chose to train independently. On the right side of the diagram, we see how the model processes language using the LCM, Large Concept Model, framework, which works like a sandwich. Bottom layer, concept encoder. This fixed layer converts regular words into abstract concepts or complete ideas. Think of it as transforming text into a universal idea language. Middle layer, large concept model. Here, the model processes and understands these concepts by focusing on their main ideas rather than individual words. Top layer, concept decoder. Finally, this layer converts the processed concepts back into words, making them readable and understandable. This process is similar to taking a story written in one language, converting it into universal symbols that can be understood in any language, processing the ideas, and then translating them back into words for a specific language. The key innovation here is that, unlike traditional AI models that work directly with words, this system works with complete ideas or concepts, making it a more abstract and versatile approach. What's really fascinating about this is that they mention how, to some degree, the architecture of the large concept model aligns with the VJEA approach developed by Yann LeCun, one of the leading figures at Meta AI. This VJEA approach focuses on predicting the representation of the next observation within an embedding space. It's intriguing because VJEA is a groundbreaking architecture in its own right. This section discusses a new architecture designed for self-supervised learning, focusing on how it aims to mimic the way humans learn.
The goal with JEPAs, which means Joint Embedding Predictive Architectures, is to create highly intelligent machines that can learn as efficiently as humans. VJEPA is pre-trained on video data, allowing it to efficiently learn concepts about the physical world, similar to how a baby learns by observing its parents. It's able to learn new concepts and solve new tasks using only a few examples without full fine-tuning. VJEPA is a non-generative model that learns by predicting missing or masked parts of a video in an abstract representation space. Unlike generative approaches that try and fill in every missing pixel, VJEPA has the flexibility to discard irrelevant information, which leads to more efficient training. To allow our fellow researchers to build upon this work, we're publicly releasing VJEPA. We believe this work is another important step in the journey towards AI that's able to understand the world, plan, reason, predict, and accomplish complex tasks.
If we take a closer look at the results, we can see that LCMS consistently produced coherent and meaningful expansions. It also demonstrated a significant advantage over LLMs like Llama 3.1a by avoiding excessive repetition. Furthermore, LCMS showed better adherence to instructions, creating more controlled and precise length expansions. Overall, I find this particularly fascinating because tokenization has long been a major challenge for LLMs. Even small issues in AI can have a big impact, and LCMS seems to address some of these effectively. Thanks for watching. Don't forget to like and subscribe. See you in the next part.